So this talk is about nitrous oxide. It's a hot topic right now, so a lot of things are changing. It's so new that also a lot of new things are published every month, even every quarter. Like 2 or 3 years ago, we didn't hear a lot about that, but it really changed a lot, and at a rapid pace, many countries are looking into the topic. The topic of today is indeed a little bit initiating a discussion on how should we go forward, and can we maybe speed up the process based on our discussions with our customers, with a lot of utilities, and how things are being done. So it's about mechanistic understanding, really understanding what happens there, and then using that knowledge to really mitigate effectively. So that is really the topic of today. It's a collaboration with a lot of colleagues, and of course there are a lot of authors behind the scenes as well that are not on this presentation. So global status, it has been presented a couple of times. I will not spend too much detail here. These colors we have put, so it's not based on a formal research, but it's based on a lot of conversations we have with the market. And then you feel a lot is changing. So dark blue countries are, for example, countries that have at the national scale really a discussion going on already. And it's changing so fast because I had a conversation with Sina from IVL. Sweden, for example, will also start with a national initiative. I heard this morning from Australia and New Zealand, they will join forces, 20 plants. And Netherlands is going to start a national initiative of 50 plants of monitoring. So it's really going so fast that these maps will change continuously. And you have other emerging countries as well. So don't take it too literal. It's just that thing that it's moving. So what we heard from our customer in New Zealand is we simply have no choice. We can't achieve net zero targets if we don't tackle process emissions. Because 5 years ago they did a whole quantification. 8% was process emissions like nitrous oxide, methane. But then they did a whole, that was with old emission factors. Then they did a new investigation, and the current numbers is 50 to 60%. So if they don't reduce those, they can simply not reduce, and they have stringent 2030 emissions. So actually observations are, we are now working on the topic for over a decade. It started scientifically, and some utilities already work on it for over a decade, which is really early. On-site data collection has matured a lot. It created a lot of awareness, a lot of discussions, which is great. But now we ask ourselves the question, we should really, can we investigate how we can accelerate this process? Yeah, to especially not only assess, but also reduce the initiatives, because 2030, 2035 is not a lot of time. Huh? Can we accelerate that? And the question is, if we keep doing what we do up till now, can we expect the same, more of the same? So can we also maybe bring in some additional insights that can accelerate the process? We did some questioning of the market recently, and these are some challenges related to assessment of your baseline emissions. For example, more than half of the utilities, they say, yeah, reliable quantification of emissions is really of concern. Reliable quantification. And also the on-site data collection, processing, the analysis is not a walk in the park. And people that work with N2O probably will know this. Cost is less of an issue right now. It's really these two topics there. There are specific challenges. How to quantify your yearly emissions. You have to monitor for 5 years. Where do you put your sensor? There are really specific questions. Now, on the mitigation end, there are also specific challenges. For example, what are the right mitigation measures for our plants? Because it is, one thing is known. It is very plant specific. So, and the question is, how do we know, if we run 5 plants, how do we mitigate? And then also the on-site testing of these measures is also not a walk in the park, because sometimes people do tests, but it's so hard to prove with your sensors or your measurements if you're literally mitigating. It's not always that easy. And maybe you are, maybe you're not. So that's some other challenges. Yeah, how to rapidly evaluate the measures. Like, what are the possible measures we can take? How do we confidently report on the % reduction, because that will be the next step, and things like that. So one of the key conclusions of one of the sessions at the World Water Congress in Copenhagen was we have to keep measuring and measure more. And that was actually yesterday in the IWA webinar on greenhouse gas emissions, a little bit of the same direction. It's good, we definitely need more efforts, we need to collect data, we need to know what we are talking about, but we what we want to add is also, it's a bit of a criticism, but I don't want to offend anyone, but we just want to evoke some discussion. So 1 decade later, what our industry as a whole, not one utility, but what our industry as a whole knows about mitigating N2O at full scale, not at pilot scale, at full scale is rather disappointing. So the question we ask ourselves is, how do we really expand our toolbox as such that we can accelerate these efforts? Because the question is, if we do measurements at 20 more, 50 more, 60 more plants, will it really, it will definitely lead to new knowledge, definitely. But the question is, at the right pace, is it in proportion to the investments, and can we literally mitigate that, right? These are the key questions. So one of those tools we are looking very actively into is mechanistic models. So what are mechanistic models? For example, you have the kinetics. This is nitrification, denitrification. So these are the autotrophs, these are the heterotrophs. I should not educate you on wastewater treatment, but of course there are 3 pathways of N2O production. 2 are the autotrophs, here and here under specific conditions, and then the heterotrophs can also produce an N2O. But of course this is not a disaster because it's inherent to denitrification. So they also eat a lot of the N2O. But just remember, we have 3 pathways, 3 sources of N2O, and it depends on the local conditions. So what are local conditions? You can look at them in 3D, for example with a CFD simulation, which is a 3D simulation of your water flow, with your bubbles, and then you can add the kinetics, and if you add the kinetics, you can literally visualize in 3D your concentrations, including N2O. Not only N2O, you can even quantify which pathways, which bacteria are producing where, which fluxes. Of course it's a model, but it's always an uncertainty, but it gives so much good understanding on what to do. So that's a 3D simulation. And of course, you also have models that look dynamically. For example, what are the peaks, the N2O peaks? This is data from a real plant, and you can see the fluctuations are huge, and this is not new information, of course. But the models can predict these, at least some of these fluctuations, and we can look at them. So we have spatial models, temporal models, and this is an example from a Canadian reactor. I'm just going to play a movie. Look at the gas concentration of N2O that's being stripped and how it shifts according to what we change. It can be operation, it can be influence, it can be your aeration rates. But the thing is, this is how dynamic it is. Of course, it's hard to know with a one sensor how dynamic and in 3D it is, but this is reality, how things shift in a plant. So it's highly dynamic, quite complex how these zones shift. So one thought here on sensor location and data interpretation. So a bioreactor is like a coffee cup. Everybody knows this. Maybe not. Don't try this at home to cut it in half. Will not work, I think. But anyway, it takes some time to mix your milk. Huh? I typically also explain to people, if you take a bath and everybody pours in some new warm water, it takes a while. You literally have to stir with your arm quite a lot. Of course, these are systems of thousands of cubic meters. So they are never perfectly mixed. It's really impossible. It's economically infeasible, and it doesn't make sense. Now, the result of that is we have gradients. This is, for example, a gradient of dissolved oxygen, and we have validated this model, so I can definitely send you some information, but we literally validated it with a 3D measurement campaign years ago. So these gradients exist. They can be 200, 300% in one cross-section. Depends on a lot of factors. But inherently, this leads to gradients in N2O as well, of course, obviously. So this is a real reactor from the Netherlands. We are looking from the top here, and this is the ammonia profile from the top. We just cut it in half, let's say, and this is the same gradient of the nitrous oxide in the liquid phase. So yeah, you can see, of course, ammonia gets oxidized. That makes sense, it reduces. And then your N2O gets produced, and it travels like that. It gets stripped, and the concentration decreases. Now, there are a couple of observations to be made. One, this is a dead zone, so there is a zone apparently in this reactor with very low N2O levels. Just imagine your sensor would be moved with a few meters, this or this. It makes a lot of sense, like a lot of difference. But more interesting is if we look at the side view, for example, in this specific system. So here you have the influent coming in, the return activated sludge, and the internal recycle. The two streams are supposed to mix. They don't really do it very well. So you can see the blue stream goes under this red one, and it takes a while. They go like this, and they are ultimately pushed to the aeration like this. When you look from the side, at the location where the sensor is located, the sensor in the anoxic zone, which is actually used to calculate the emissions, then you can already see that you have a gradient, a vertical gradient, in this only 4 meters depth reactor. It's not really a very deep system, of 30%. So it means if you do a sensor reading here, in this case it is not representative for the real flow coming through. It is simply a huge uncertainty. Now, you can say, well, this is detailed, these simulations, but the question is, can we really neglect these things if we want to know what we are doing in the future? This is not exceptional. We see it a lot. We have modeled over 100 reactors at the global scale with this model. So it happens. And then you can use the same model, for example, to fix the mixing. Just imagine you fix the mixing here, you do something, the mixing is okay, and then you can see this dead zone disappears, and your reading is very different. So it's like a 31% difference. Yeah. The resulting reading. Simulated. Now, that was on the sensor location. Now, on the mitigation and the quantification of your baseline. So this is a reactor from Watercare in New Zealand. This is, again, the top view. The water goes like this. Anoxic zone, aeration, starts here, and it goes like this. Aeration, it's all aeration. So this is, again, the liquid phase N2O concentration, the simulated. So that's the color gradient here, high to low. And you see the stripping happening again, yeah? So it turns dark blue. Now, the interesting thing is, just imagine you would have your sensor here and quantify your emissions based on the sensor or with the model. It leads to quite a big difference in this case, so 40%. Now you can, of course, we can debate a lot who is right. Probably reality is somewhere in between or somewhere, but yeah, that's really a big question. It's 40%, who is right? Now, why are they different? That's an interesting question. Well, you would assume everything gets stripped, so it goes downstream, it gets stripped. Why is the model giving lower emissions in this case? Because a lot of the N2O is being consumed in the aerated zone. It's not all getting stripped, and it's really significant. This part is getting eaten up in the aerated zone. Because of the dissolved oxygen, I'm not plotting it here, has a huge gradient. It's quite low in certain zones. So you cannot simply assume complete stripping. That's one thing. So biological factors are not taken into account. Now, something interesting happens when you mitigate. Just imagine you extend the anoxic zone and you push the air more here. So same airflow rate, but some more volume for denitrification. You get rid completely of this yellow zone. So you don't have this spike of autotrophic organisms giving this boost in N2O. The interesting thing is, with the sensor, you would never capture this. So with the model, you would see a 30% reduction, but the sensor is actually upstream of that zone, so your baseline was different. Don't get me wrong, my message is not our measurements always over-predicting or under-predicting. I'm just saying that the differences can be big, and we should just be cautious how we interpret things. This is another example from a recent project where we are using a dynamic model right now. It's not a surprise that you can indeed, with smarter carbon dosing, mitigate these big peaks. So that's what we are doing now, and in this case it leads to drastic mitigation, as you can see. They will implement this system, so they already had an idea about the COD-N ratio, but now they can really implement these changes in their plant, in their control. But what I also wanted to say is very recent, this result, is that the model also in quantitative terms starts getting very close to measurements right now. We are very much working on this, but it was a non-calibrated model, so we didn't tweak these parameters yet. And so quantitatively, we are getting close. Okay, so what are the conclusions of my presentation? We neglect, in the current way of working, we really neglect some fundamental physics and biochemical pathways. This also means, for example, just imagine you use liquid sensors to assess emissions. Theoretically, you can prove that it's impossible to close your mass balance, because if you don't measure your off-gas, you can never capture the fact that there is production and stripping simultaneously in an aerated zone. Yeah, it's a very, I know it's a very, we need to discuss it's maybe some technical things, but there are some essential physics and biology we might have to consider in the future. the models I think we use can really use to speed up. We use to speed up the knowledge gap we have because the learning curve is so steep, and we heard it. So there is more stringent effluent limits to be expected. There is a challenge of micropollutants. Now this comes on top of it, N2O. So the question is, can we not have this trading process way more efficient by adding an additional tool, doing it that way, and to really speed up the learning. So the models are also not a very experimental thing. So we have applied the kinetic model at over 100 wastewater treatment plants, and we are currently now doing it at more than 20 plants for N2O only. So it's really not it's quite a validated solution. So we also believe we could increase the accuracy of direct monitoring by complementing this, or also maybe reducing measurement efforts in some cases. So it's all food for thought. And we also will use the existing data at plants to really validate the models and build the trust, because we believe this will be needed. Yeah, we are a sector relying a lot on measurements. If we use models to make certain decisions, it will help if we can build the trust by showing these models are accurate. So these mechanistic models have the laws of physics and biology integrated. So this also means they are more robust and widely applicable across plants. Just imagine you have data collection at one plant and you train an ML, machine learning model based on that. That same model cannot readily be used at a different plant because it's trained on that plant. Yeah, that's a fundamental difference between those models. But what is very important is that it contributes to the other challenges as well. For example, we don't only do let's say N2O focused projects, but in many cases the question is, how do we make optimal use of our existing bioreactor? Can we get lower effluent limits with the existing system, while also maybe mitigating N2O? Yeah, so it's not a one-one question. So yeah, we try with our company in collaboration with a lot of parties in the market to really accelerate our path to net zero, and we believe for the new national initiatives to start, that this might be a very good part to add. Because it will really change a lot how we look at the plants. Okay, so thanks so much for listening.